Alright, hello everyone. I hope you guys are doing good. So today I'm going to be discussing the solutions to this Codeforces Round 772. This was a Division 2 round held yesterday. Talking about the round, I think this was a really high quality round. The problems were very good. The first three problems were okayish, but specifically problems D and E, they were like really interesting. And the best part is that they didn't require some very advanced algorithms. Everything that was used in these two problems was very well known to like almost all the contestants, but even then these problems aren't intuitive. So that's the beauty of this set. I think I really enjoyed the round, and the problems were very high quality. So there's that. So today I'll be discussing the first 5 problems from A to E. So without any further ado, let's start with problem A. So in this problem, we have an array of size n, and we can perform the following operation. We will choose two distinct indices I and j, where I is less than j, and we'll replace ai with any integer x and aj with any integer y. And the condition that needs to be satisfied is that the bitwise OR of ai and aj should always be equal to the bitwise OR of x and y. And by doing this operation, our final goal is to minimize the total sum of the array. So yeah, that's what we want. We need to do this operation. We are free to do it as many times as we want. But at the end of all the operations, we need to find the minimum sum of all the elements of the array that we can get. So that's the problem. Let's see how we can solve it. It's really a very easy problem if you have some common knowledge about bitwise operators. But I think it's not a very good practice to give a problem A as a bitwise operations problem, because a lot of people don't really know about them. So a lot of people won't even be able to solve it. So I don't think it's a very fair thing to do, but it is what it is. If you have some common knowledge about bitwise operations, then this is obviously a very trivial problem. So let's see. So we have two indices I and j, and we can replace ai with x and aj with y, such that ai or aj is equal to x or y. And by doing this, we need to minimize the sum of all the elements of the array. Now how do we do it? So initially, let's just take two elements. Let's just fix I and j, and let's try to see how we can minimize the sum of these two elements. Let's forget about all the other elements of the array. So let's say we have fixed some I and fixed some j, and we are choosing some x to which we can replace ai with, and some y with which we can replace aj with, such that x plus y is the smallest possible. Okay. So what we do is, obviously, we look at the binary representation of ai and aj. So we look at the bits of ai and aj. So what happens is that if we found any bit which is set in either ai or aj, it has to be set in the bitwise OR of ai and aj, and so it has to be set in the bitwise OR of x and y. So if a bit is set in either ai or aj, then it will be set in ai or aj, and consequently in x or y as well. So now we know that this particular bit will be set in x or y, and we need to choose the values of x and y in such a way that the sum x plus y is minimized. So how do we do it? Well, the best thing to do is to set this bit in x and not set this bit in y, or vice versa, right? So the best thing to do is to make the bit set in x and not set in y. So that's what we are going to do. For any bit which is set in either ai or aj, we'll make it set in x and we'll make it not set in y. That way the sum is minimized and the condition of the bitwise ORs being equal is not broken as well. And so if we keep doing this, what happens is that our y becomes 0 and x becomes nothing but ai or aj. So if we look at only two elements, we have proved that the best thing to do with these two elements is to take x is equals to ai or aj and y is equals to 0. And so this basically completes the solution. Now what we can do is that we can fix I is equals to 1 and iterate j from 2 to n. If we do it, what happens is that we will keep converting AI to the bitwise OR of AI and AJ. So initially AI will become AI or A2 and A2 will become 0, and then A1 will become A1 or A2 or A3, and both A2 and A3 will become 0. And similarly, when the process ends, A1 will become the bitwise OR of A1, A2, A3 up till AN, and rest all the elements will become 0. And so the final answer that we'll get is nothing but A1 or A2 or A3 up till AN. And so this is the minimum possible sum. Obviously we cannot achieve a sum which is lower than this because of this condition that if we look at the total bitwise OR of all the elements, it has to be conserved because the operation never changes the bitwise OR. So like this operation is never changing the bitwise OR of all the elements of the array. And so the minimum sum that we can get using that bitwise OR is nothing but this bitwise OR itself. And so the final answer is going to be A1 or A2 or A3 up till AN. So that's it. Let's just have a look at the code. The code is pretty trivial. If you find any bit which is active, you add 2 raised to the power that bit to your answer. Also, you can simply calculate the bitwise OR as well of the entire array and output that. That will work fine. So yeah, this completes the solution to problem A. Pretty trivial. Let's move on to the next problem now. Problem B. Just a moment. Yeah. Moving on. So in this problem, we have an array A of size n, and each element is between 1 and 10 to the 9. And again, we are allowed to perform certain operations. And in an operation, we can replace an element with any integer between 1 and 10 raised to the power 9. So yeah, basically you can change any number of the array, keeping in mind that the number doesn't exceed these limits. So what you need to do is you need to output the minimum number of operations that are needed such that the resulting array does not contain any local maximums. And you also have to return the final array after those number of operations. The definition of local maximum is that an index I is a local maximum if AI is strictly greater than AI minus 1 and AI is strictly greater than AI plus 1. So the problem statement is simple enough. We are allowed to change any element to any other value, keeping in mind that the value is within these constraints. And finally, we need to output the minimum number of operations such that such that after doing all the operations, there are no local maximas present in the array. So we need to output the minimum number of operations as well as the final state of the array after doing all the operations. So yeah, that's the problem. Let's see how we can solve it. So we can change any element to any other, and we need to eliminate local maximas, and that's it. So we need to eliminate local maximas in the minimum amount of operations possible. So let's see how we can do it. So the main process here that we'll follow is that we will iterate from left to right, and we will eliminate all the local maximas that we get in this order. So we will iterate from left to right and keep eliminating all the local maximas. And in the process, we will change the values in such a way that later on that particular change will be as helpful to us as possible. And obviously that algorithm will be correct. So yeah, we are iterating from left to right, and let's say we have already eliminated all the local maximas in the prefix from 1 to I minus 1, and now we realize that the ith element is also a local maxima. So what happens is that we are at an index I, and we notice that AI minus 1 is smaller than AI and AI is greater than AI plus 1. Obviously this is a local maxima. Keep in mind that I have already eliminated all the local maximas which are present in 1 to I minus 1. And now I need to change one of the three values, either AI minus 1 or AI plus 1, such that this AI is no longer a local maxima, right? So let's write it down. So we need to change at least one value among AI plus 1 and AI minus 1 such that AI is no longer a local maxima. Because if we don't do this, then we will end up with an array in which ai will be a local maxima, which is not allowed. We always have to make sure that the number of local maximas is 0. So obviously we have to change one among these three values, but we need to change the value in such a way that that particular change will be most helpful to us later on. So we have to change one of the values in such a way that the change will be most helpful to us later on. Okay, so let's see which value we should change such that the change is most helpful to us. So let's look at a of I minus 1. So I am already done with removing all the local maximas in 1 to I minus 1. And so the only index at which a of I minus 1 is having an impact is I. And so if I change a of I minus 1, I can affect at most one index. So if we change I minus 1, we will impact on only index I. But if we change I, what happens is that we will have an impact on index I as well as index I plus 1, right? So like because we have already eliminated all local maximas in 1 to I minus 1, those particular indices are useless to us. So we only need to have a look at the indices from I to n. So we will impact on indices I and I plus 1. Like we can change the state of a of I plus 1 being a local maxima if we change a of I. Similarly, if we change I plus 1, then we can have an impact on I plus 1 as well as I plus 2. So we will have an impact on I plus 1 and I plus 2. And so this basically proves that it is always optimal to change a of I plus 1 because it will have the maximum impact and it will be the most helpful operation for us later on. And so it is proved that we will always change a of I plus 1. Right. So with this in mind, now let's see to what value we should change a of I plus 1. Okay, so for that we'll make two cases. So case 1 is that a of I plus 2 is greater than a of I, or case 2 is that either I plus 1 is equal to n, that means I plus 2 doesn't exist, or I plus 2 equal to like a of I plus 2 is equal to a of I. Sorry, not equal to, less than. Yeah, so these are the two cases. Let's just get rid of this case because this is a trivial case. So yeah, the case 1 is that a of I plus 2 is greater than a of I, and case 2 is a of I plus 2 is less than a of I. In these two cases, we have two different possible changes that we can make to a of I plus 1, which will be optimal. So let's see. So in this particular case, what we notice is that let's say this is the ith index and this is somewhere here. And since ith index is a local maxima, I plus 1 will be somewhere here. And now we know that a of I plus 2 is greater than a of I. So a of I plus 2 will be somewhere here. So what we notice from this is that if we change a of I plus 1 to a of I plus 2, what happens is that neither a of I plus 1 can be a local maxima, nor a of I can be a local maxima, nor a of I plus 2 can be a local maxima. So if we change a of I plus 1 to a of I plus 2, it impacts all these three values and it makes sure that none of these three values become a local maximum. So it is the best that we can do. And so the thing that we'll do here is that assign a of I plus 1 to be equal to a of I plus 2. Right? Similarly, let's look at the second case. So now we have a of I here and we have a of I plus 1 here, and a of I plus 2 is less than a of I, so let's just assume a of I plus 2 is somewhere here. So now what happens is that if we assign a of I plus 1 equal to a of I now, so what happens is again a of I cannot be a local maxima, similarly a of I plus 1 cannot be a local maxima, and since a of I plus 1 is greater than a of I plus 2, a of I plus 2 will also never be a local maxima. And so it is optimal to assign a of I plus 1 is equal to a of I. And that's it. These are the two cases that we need to take into account, and this basically completes the entire solution. That's it. Let's just have a look at the code. So a very simple code. We just iterate from 2 to n minus 1, and we see whether we find a local maxima or not. And if we find a local maxima, then this is the trivial condition that I plus 1 equal to n. Here we can simply change a of I plus 1 to a of I, it doesn't matter, and increment our answer. Otherwise, we will check if a of I plus 2 is greater than a of I, we will change a of I plus 2, a of I plus 1 to a of I plus 2. Otherwise, we'll change a of I plus 1 to a of I and increment our answer. And that's it. Finally, we'll output the answer and the modified array as well. So that completes the solution to problem B. Moving on, let's now talk about the third problem. Okay, so let's see. Again, we have an array of n elements, and yet again we are allowed to perform certain operations. So in an operation, what we do is we select three indices x, y, and z, such that x is less than y is less than z is less than equal to n. And what we do is we replace a of x with a of y minus a of z. And after this operation, the absolute value of a of x has to be smaller than or equal to 10 raised to power 18, obviously. And our goal is to sort the array in non-decreasing order, and that's it. So we have to sort the array in non-decreasing order, and to do that we can perform this operation as many times as we want. Replace ax with ay minus az, where x is smaller than y is smaller than z. And we also need to output all the operations that we do, and that's it. So we need to tell whether or not it's possible to sort the array, and if it is possible, we also need to output all the operations that we perform. So yeah, this is the problem. Again, the problem statement is small and easy to understand. So that's another good thing about this round. So now let's talk about the solution. Okay, so let's make the first observation. So the first observation is that we can never change the values at indices n minus 1 and n. Why? Because to apply any operation at an index x, we need at least two indices which are greater than x. So the first observation is that we can never change a of n minus 1 and a of n. And so since we can never change them, we need to sort the array. So we need to make sure that a of n minus 1 has to be less than or equal to a of n, because if that's not the case, then the array can never be sorted, obviously. And so if a of n minus 1 is greater than a of n, then the answer is simply minus 1, because the array can never be sorted. Simply because we can never change a of n minus 1 and a of n, the final array has to be sorted. So a of n minus 1 and a of n both need to be in sorted order initially. So there is that. And now let's make two cases, and let's just get done with this problem in those two cases. So case 1. Case 1 is that a of n is greater than or equal to 0, and case 2 is a of n is less than 0. So in the case when a of n is greater than or equals to 0, there is a very straightforward solution to this problem. And that solution is that for all I from 1 to n minus 2, perform the operation I, n minus 1 and n, and this will just sort the array. How you ask? Well, it's very easy. We already know that a of n minus 1 is less than or equal to a of n, right? And so if we choose y is equal to a of n minus 1 and z is equals to a of n, what we get is that, so in the operation I, n minus 1, n, we will assign a of I as a of n minus 1 minus a of n. Now, since we know that a of n is greater than or equals to 0, a of n minus 1 minus a of n will be smaller than or equal to both of them, right? So since a of n is greater than or equals to 0 and a of n is greater than or equals to a of n minus 1, the value a of n minus 1 minus a of n will be smaller than or equal to both a of n minus 1 and a of n. And since we are assigning this value for all the indices from 1 to n minus 2, and they have already very conveniently said that we need to sort the array in non-decreasing order, not in strictly increasing order. So all the elements from 1 to n minus 2 can very well be equal. And if all the elements are less than a of n minus 1 and a of n minus 1 is less than equal to a of n, then voila, we have a sorted array, right? And since a of n is greater than or equals to 0, a of n minus 1 minus a of n is basically means that we are subtracting a positive quantity from a of n minus 1. So the result will be smaller than a of n minus 1. And if it's smaller than a of n minus 1, it will automatically be smaller than a of n. And so we can just do this operation. All the elements in 1 to n minus 2 will become equal. And a of n minus 1 is already smaller than a of n. And we have our sorted arrangement. And so, yeah, for the case where an is positive, we can easily do this using this operation. Now coming to the second case where an is negative, and the most interesting claim that I'm going to make here is that the answer is always equal to minus 1 if a of n is negative. And now I'm going to prove this. So the proof is not really very difficult to understand. So let's see what's going on. So let's start with the proof. So the first thing is that since a of n minus 1 and a of n are never changing and a of n is negative, so if we want the final array to be sorted, then all the elements obviously have to be negative. So all the elements in the final sorted array will be negative, right? Also, before we do all this casework, obviously the first thing is that if the array is already sorted, then the answer is 0. If already sorted, then answer is 0. I'm assuming here that the array is obviously not already sorted. So we have gotten rid of that case when it's already sorted. So yeah, let's just get that off. Yeah, so now since a of n minus 1 and a of n are never changing and they both are negative, then that means the final sorted array, if it is possible to have it, then all the elements have to be negative for sure. And now the second thing is that since the array is not already sorted, we will perform greater than 0 operations to make it sorted, right? Since it's not already sorted, the only way we can make it sorted is by performing some operations, right? So yeah, so we will perform some positive amounts of operations here. So now what happens is that let's have a look at the last operation that we perform. So let's look at the last operation that we perform. So let's say that the last operation is performed within 3 indices x, y and z. So this last operation does assign ax to ay minus az. That's what happens in the last operation. And since this is the last operation, what we can notice is that before doing this operation, both ay and az are negative. Now since both ay and az will obviously be negative because this last operation doesn't change ay and az, and the final value of ay and az has to be negative. So before doing the last operation, obviously both ay and az are negative. But if both ay and az are negative, then ax is equal to ay minus az. This value cannot be smaller than both ay and az. Also notice here that x has to be less than y, which has to be less than z. And this claim is again very easy to prove, that ax will not be smaller than both ay and az. I'll prove that, but if we just assume that this is true, that ax is not smaller than ay and az, then we have this condition that x is smaller than y and z, but a of x is at least greater than either ay or az. and so that means the array is not sorted. So now all that is left is to prove that a of x will always be greater than either ay or az or both of them. And that proof is again very trivial. Since both ay and az are negative, what happens is that if we choose ay, if we assign ax as ay minus az, actually what we are doing is that we are taking minus modulo of ay, right? Ay is negative, so ay is basically just minus modulo of ay, and from this we are subtracting minus modulo of az. So if we open this, this is nothing but minus modulo of ay plus modulo of az, which is obviously greater than ay, because we are taking a negative number and we are adding something positive to it, so it will obviously be greater than ay. So this basically proves that ax will be greater than ay. So ax is greater than ay, but x is less than y. That means that array is not sorted. So thereby I have proved that if we are performing some non-zero operations, then the array can never be sorted, because if we do this last operation x, y, z, then ax will always be greater than ay. So hence, if the value of an is negative, then the only way the answer exists is that the array is initially sorted. And that's it. So that completes the entire solution. Let's just have a look at the code. Code is again simple. If the array is initially sorted, we simply output 0. Is sorted is a very common C++ STL function that you can use in situations like this. And now if an minus 1 is greater than an or an is negative, then we output minus 1. And now if that's not the case, we can simply just do this operation for all I from 1 to n minus 2, do this operation I, n minus 1 and n, and that will do our job. So that's it. So we are always doing n minus 2 operations, which is strictly smaller than n, which is good. So that's it. That completes the solution. Now let's move on to problem D, which is the more interesting of the problems. Okay, let's see what this has to say. So here we have an array of A consisting of n distinct positive integers, and now we are building a set S which contains all the integers x which satisfy at least one of the following conditions. So either x is equals to ai for some I from 1 to n. So basically we put all the elements in the array A into our set initially, and then what we do is that if x is equals to 2y plus 1 and y is already in the set S, then we put x in the set S as well. Similarly, if x is equal to 4y and y is already in set S, then we put x in the set S. So essentially what's going on is that initially our set contains only the elements from this array, and then what we do is for all the elements we keep adding 2y plus 1 and 4y for all the elements y which are in the set, and we keep doing this for an infinite amount of time. So yeah, that's the process that's happening. And finally, what we need to tell is we need to tell the number of elements in the set S which are strictly smaller than 2 raised to the power p. It might seem very random right now, but once we realize the logic to this problem, we'll see how exactly this 2 raised to power p thing is helping us, provided these values 2y plus 1 and 4y. Also, something to notice here is that the constraints for p are really huge. There are 2 into 10 to the 5. So obviously this number 2 raised to power p cannot be kept as it is. Like, we can't really compute it, it will overflow. So we have to do something smart here. And also we don't need to tell the actual number, we need to tell it modulo 10 raised to power 9 plus 7, obviously, since the number of numbers will be very, very huge. So yeah, we need to compute modulo 1e9 plus 7, the total number of elements which are in the set S and which are strictly smaller than 2 raised to the power p, where p can be as high as 2 into 10 raised to the power 5. Another thing to notice here is that all the elements which are provided in the array initially are only up to 10 to the power 9. They are not very huge. So they are not in the range of 2 raised to the power p, where p is 2 into 10 to the 5. And this fact is actually going to help us solve the problem. So yeah, I hope the problem statement is clear enough. Let's now move to the explanation. Okay. So the process is something like this. We put all elements in the array in our set. Then for all y, so then for any number x, if x is odd and x minus 1 upon 2 is in the set, we put x in the set. Like this statement which I have written here is similar, this it is exactly the same as writing this statement, x is equals to 2y plus 1 as y is in the set. Similarly, if x is divisible by 4 and x by 4 is in the set, we put x in the set. So we need to tell the number of elements in the set strictly smaller than 2 raised to the power p. So that's the problem. Now, obviously, since the value of p is greater, since the value of p is very large, but still it is not like it is in the limit that we can iterate on it. And since we have to output everything modulo 10 to the 9 plus 7, there are two things that all this information hints us towards. First, that we can somehow make use of dynamic programming, because we need to output this modulo to 10 to the 9 plus 7, and it doesn't seem like there is any combinatorics related solution here. So it might be a good idea to use dynamic programming here. And the other thing is that we can iterate on this value p, since it's only up to 2 into 10 to the 5. And so these are the two things, key takeaways from the constraints of this problem. So yeah, let's try to iterate on the power of 2 raised to the power I. So what we'll do is, we will use dynamic programming, and let's try to define the state of our dp. So dp of I, let's say that dp of I represents the number of numbers in the set such that a number of numbers which are greater than or equals to 2 raised to the power I minus 1 and strictly smaller than 2 raised to the power I. So the range in which these numbers belong is 2 raised to the power I minus 1 closed to 2 raised to the power I open. So dp of I is number of numbers in the set in the range this 2 raised to the power I minus 1 to 2 raised to the power I. 2 raised to the power I minus 1 is closed and 2 raised to the power I is open, and we will later on see why and how I have decided to keep this range open and closed. One hint is that we need to output the numbers which are strictly smaller than 2 raised to the power p, so it makes sense to make this range to be open from the right hand side, and there is no reason for us to close it from the left hand side. So yeah, this is why we keep this range like this. So now let's try to find a relation between dp of I and the other dp values, and that's where things become more interesting. So let's say that this is 2 raised to the power I minus 2, this is 2 raised to the power I minus 1, and this is 2 raised to the power I, right? So this is 2 raised to the power I, this is like 2 raised to the power I minus 1, and this is 2 raised to the power I minus 2. So what we'll do here is we'll try to find a relation between dpi, dpi minus 1 and dpi minus 2. Okay, that's our final goal. Similarly, this is 2 raised to the power I minus 3, right? I'm not writing it down. So there are a few numbers here which will be in our set. Similarly, there are a few numbers here which will be in our set. And similarly, there will be a few numbers here which will be in our set. Now, for any number, so the range in which we are interested in is this range from 2 raised to the power I minus 1 and strictly smaller than 2 raised to the power I. So we need to find the number of elements in this particular range. Okay. So let's see how we can find that out. So any number which is in the our set and is also in this range of 2 raised power I minus 1 to 2 raised power I, there are just 3 possible cases. So case 1, the number is in the array itself. So if the number is in the array itself and it is between 2 raised power I minus 1 to 2 raised power I, it will contribute to dp of I. Okay. Case 2. Obviously now the number is not in the array itself. So either it is odd. So let's say the number is y. So either y is odd and y minus 1 upon 2 is in the set. And case 3 is y is divisible by 4 and y by 4 is in the set. So these are the only 3 possible cases. So we can just naively count the total number of elements which are in the array and which belong to this range. So that is not going to be a problem. So we can just count that out. So now let's try to find out the total number of values of y which are odd such that y minus 1 upon 2 is in the set. Okay. So what we notice here is that if a number y minus 1 upon 2 is in the set and y belongs to this range of 2 raised power I minus 1 to 2 raised power I, then y minus 1 upon 2 will always belong to this range, 2 raised power I minus 2 closed to 2 raised power I minus 1 opened. Why? Let's see. So we are back to case 2. So if y minus 1 upon 2 belongs to the range of, so this belongs to our interested range, which is 2 raised power I minus 1 to 2 raised power I, then y always belongs to this range, 2 raised to the power I minus 2 closed and 2 raised to the power I minus 1 open. And this is very easy to prove. Why? Because if we take this left hand limit 2 raised power I minus 2 and if we do 2y plus 1, if we do 2x plus 1 from here, what we'll get is 2 into 2 raised power I minus 2 plus 1, which is 2 raised to the power I minus 1 plus 1, and which clearly belongs to this range. And similarly, if we do this, if we take this right hand limit 2 raised power I minus 1, we take 2 into x plus 1, then what we'll get is 2 into 2 raised power I minus 1 plus 1, which is nothing but 2 raised to the power I plus 1, which is outside our range. And so that is why this interval is open and not closed. So yeah, any number which is of the form y minus 1 upon 2, like that number has to be present in this particular range such that it can contribute to any number in our interested range, which is 2 raised power I minus 1 to 2 raised power I minus 2. And we already know that the number of such numbers is what? dp of I minus 1, right? The number of numbers which belong to the set and also in this range is nothing but dp of I minus 1. So from case 2 we get dp of I minus 1. And now let's come to case 3. And here what I claim is that the case 3 is obviously if y is divisible by 4 and y by 4 is in the set. So if y by 4 is in the set, then this should be y minus 1 upon 2 here, I'm sorry. Yeah. Sorry, so this should be y. Yeah. So if y belongs to 2 raised power I minus 1 and 2 raised power I and y is odd, then y minus 1 upon 2 should belong to this particular range, and that particular value of y minus 1 upon 2 will give me a value of y. Okay, so coming back here, so now I am claiming if y belongs to 2 raised to the power I minus 1 to 2 raised to the power I, this is open, and y by 4 is in the set, then y by 4 always belongs to this range, 2 raised to the power I minus 2 closed, 2 raised to the power I minus 3 closed to 2 raised to the power I minus 2 open. And this range is nothing but dp of I minus 2. And why is it so? Again, you can try to take this lower limit and upper limit, and if you take 2 raised per I minus 3 and multiply it by 4, what you will get is 2 raised per I minus 1, which belongs to our range. Similarly, if you take 2 raised per I minus 2 multiplied by 4, you will get 2 raised to the power I, which is just outside of our range. So that is why we keep this interval closed, open. So yeah, basically that is it. If we are getting 2y plus 1, then y should belong to this range of dp of I minus 1, and if we are getting 4y, then y should belong to 2 raised to the power I minus 2 to 2 raised to power I minus 3 to 2 raised to power I minus 2, which is the range of dp of I minus 2. That's it. So yeah, this is it. So let's try to write it down formally. So if 2y plus 1 is in the range for dpi, then y is in the range for dpi minus 1, and if 4y is in the range for dpi, then y is in the range for dpi minus 2. So by doing all of this, we have established a very clear-cut recursive relation by which we can define our dp. So dp of I is nothing but dp of I minus 1 plus dp of I minus 2 plus the number of elements already in the array, which are in this range of 2 raised to the power I minus 1 to 2 raised to the power I, and this is open. Okay, so now one might argue that we have a complete solution, and this is again pretty easy to code, so we can code this up and get done with the problem. But there is still one thing which is missing here, and that is that we are doing some overcounting, and that overcounting is done in such a way that if we are considering an element which is already in the array and belongs to this range, then that element can be counted twice, because that element can also come from an element from dp of I minus 2 or can also come from an element from dp of I minus 1. So we need to count it only once. So we are overcounting, and we need to somehow avoid this overcounting. And as an example, what I can show you here is that in the samples, if you look at this second test case, here are the list of values that you will get. So let's say that we are at I is equals to 5 and we are looking at all the elements in the range from 16 to 31. So you can see that here the number is 20 and the numbers are 20 and 23. So we can notice that 20 comes from the array itself because it is already present, but it also comes from 5 into 4. And since it also comes from 5 into 4, we are counting it twice. So we need to count it only once. So somehow we need to avoid this overcounting. And to do that, what we'll do is, to avoid overcounting, we will only take those elements from the array which cannot be formed from other elements of the array. For example, if you notice here, 20 can be formed from 5, and that is why we will just ignore 20. Right? So if we do that, then we are avoiding this overcounting. But the question is, how do we actually check? Well, it turns out that the checking part is not very difficult. Why? Because for any number n, we can get it only if we can either get n minus 1 by 2 or we can get n by 4. But we don't have to check for both these values because n will either be odd or even. So if n will be odd, then we can check for n minus 1 by 2, and if n is divisible by 4, then we can check by n by 4. And in both of these operations, we are at least halving n, and so in at most O of log n time, we will be able to check whether n can be formed from any other element of the array or not. And since since the number of elements are up to 10 to the 9, we can just check for each of the element present, and that check will just be an O of n log n check, and so we can do it, right? So yeah, this basically completes the entire solution. The recursive relation is dp of I is equals to dp of I minus 1 plus dp of I minus 2 plus the number of elements which are already in the range and which are in 2 raised per I minus 1 to 2 raised per I, and which cannot be made from any other element of the array. So this is the final recursive relation, and we can just code this up and very easily get an accepted verdict. So that completes the solution to this problem. Let's have a look at the code. Okay, so let's see what I'm doing here. Okay, so I have this array, and now I will make a dp array, and I will iterate for all I from 1 to p. So if I is less than equal to 33, only then I am checking whether the elements are present and whether they can be made or not. Why? Because if I is greater than 33, or we can also replace 30 here, because the elements are only up to 10 to the 9. And so if I is greater than 30, then this term in the dp will always be 0. This last term will always be 0. Why? Because any element doesn't belong to this range. So then we can simply do dpi minus 1 plus dpi minus 2. But if I is less than equal to 30, then what we'll do is we'll naively go over the entire array, and we'll see that whether or not the element lies in our interesting range of 2 raised power I minus 1 to 2 raised power I. If that's the case, we will just check first of all whether or not it's possible to get this element from any other element of the array. This check can be done easily, very easily recursively. So what I'm doing here is that I am making a recursive function, and if the element is present, then I'm returning true. Otherwise, if it's divisible by 4, then I'm checking for n by 4, or if it's odd, then I'm checking for n by 2 minus 1, n minus 1 upon 2. And finally, I'm just returning the answer. So we can very easily recursively check in O of log n time whether or not an element can be made or cannot be made from previous elements of the array. So finally, if an element cannot be made from previous elements, then I'm incrementing dp of I, and then I'm incrementing dp of I by dp of I minus 1 plus dp of I minus 2, and that is it. Finally, the final answer obviously is going to be the sum of dp1 plus dp2 up till dpp. So yeah, I am iterating from 1 to p and adding dp of I to my answer. So that completes the solution. If you are not yet clear about why this recursive relation is coming, I'll just explain it again. So any number which can be in this range from 2 raised power I minus 1 to 2 raised power I will either be of the form 2y plus 1 or 4y. So if it is of the form 2y plus 1, then y definitely needs to belong to this particular range. And if it is of the form 4y, then y definitely needs to belong to this particular range. And you can prove it very easily by taking the lower limits and upper limits and checking that 4y, if y is in this range, then 4y will be in this range. Similarly, if y is in this range, then 2y plus 1 will be in this range. And so there comes the recursive relation that dp of I is dp of I minus 1 plus dp of I minus 2 plus the number of elements which are initially in the array and in this range, minus the number of elements which can be made from the previous elements of the array. And the elements which can be made from the previous elements can be easily checked using brute force in O of log n time. And that's it. That completes the entire solution. So I hope it's clear enough why this solution is working. So that is it. That completes the solution to problem D. Now we'll move on to problem D. Problem E. So this is the last problem that we'll be discussing today. And let's just quickly see what this has to say. To be honest, if you ask me, both D and E were kind of similar in difficulty. But since D was placed before E, a lot of people tried D. But there is nothing very extraordinary in problem E as well. So let's read it. So there are n cars on a coordinate axis OX, and each car is located at an integer point initially, and obviously no two cars are at the same point. Also, each car is oriented either left or right, and every car is moving at a constant positive speed in the direction in which they are oriented. Right. So basically, I have n cars on a coordinate plane. Every car is appointed a direction and a speed, and every car is moving at some particular positive value of speed. So it is moving with some speed in the direction in which it is facing. And now we have a definition. So we have definition of two irrelevant cars and two destined cars. So two cars are irrelevant if they will never end up at the same point regardless of whatever their speed is. Okay. And two cars are destined if they will always end up at the same point regardless of what their speed is. So we have been provided with m points of information, like we have been provided with m pairs of information. A pair 1ij denotes that the cars 1 and j are irrelevant, and a pair 2ij denotes that the pair of cars I and j are destined. And also we have lost all the other information. We don't know the orientation, we don't know the speed, we don't know the position of any car. We just know this information that there are m pairs, and in every pair either the two cars are irrelevant or they are destined. And what we need to do is we need to restore the locations and the orientations of each car. And obviously if there are multiple answers, we need to output any one of them. So we need to output a valid valid orientations and positions of all the cars. By valid I mean a location. By valid I mean an arrangement which satisfies all of these m restrictions, all of these m relationships that have been provided to us. Right. So I hope the problem is clear. Two cars are irrelevant if they never meet, irrespective of their speeds, and two cars are destined if they always meet, irrespective of their speeds. And we have lost all the information, so we need to restore the orientations and the locations of every car such that all the m relationships are satisfied. Okay. We will just be provided with these relationships and nothing else. Right. So yeah, that's the problem. Let's see how we can solve it. So to begin with, first of all, let's have a look at when two cars are destined and when two cars are irrelevant. So condition for being irrelevant. So if two cars are facing in opposite directions and they are going away from each other, then obviously they will never meet. So if two cars are going away from each other at any speed, they will never meet, obviously, right? But if two cars are like moving in the same direction, then they can meet or cannot meet depending on their speed. So if cars are, so here as an example, I can say that the two cars are, the left car is moving towards the right and the right car is moving towards the left, or the left car is moving, yeah, that's the only situation that we can have, right? So the left car has to move towards the, sorry, this should be L and this should be R, yeah. So two cars are irrelevant if the left car is moving towards the left and the right car is moving towards the right. I can also like draw something like this. So this first car is moving here and this second car is moving here. So in this way, I can say that they are never going to meet irrespective of their speeds, right? So this is the condition for them being irrelevant. Also, if this is not the case, then they will never be irrelevant because they will either be going in the same direction or they will be moving towards each other. So if they will be moving towards each other, then they will always meet. And if they are going in the same direction, something like this, let's say both of the cars are moving towards the right, then whether or not they will meet, this depends on their speed. If the speed of the left car is greater than the speed of the right car, then at some point of time the left car will overtake the right car, and at that point they have to meet, right? So if both of the cars are in the same direction, then obviously they are neither irrelevant and nor destined. So this is the condition for the cars to be irrelevant. And now let's look at the condition for being destined. So similarly, the condition for being destined is that the left car should be moving towards the right and the right car should be moving towards the left. That is, both the cars should be moving towards each other, because in this case, whatever their speed may be, there will be a point of time where both of them will be in the same position. So it would look something like this. Right. So this is the condition for the cars to be destined, and this is the condition for the cars to be like irrelevant. Okay. So that's it. Now let's try to make a very crucial observation. So the observation that we make is that if the two cars are irrelevant, then their orientations should be LR, and if the two cars are destined, then their orientations should be RL. So in both the cases, if two cars have a relationship, it doesn't matter whether it is a destined relationship or an irrelevant relationship, both of them must have different orientations, right? Like if both of them are irrelevant, then it has to be LR. The left car has to be L and the right car has to be R. And if both of them are destined, then the left car has to be R and the right car has to be L. But in both these cases, we notice that it is either LR or RL. It cannot be LL or RR, right? So in other words, what we can say is that if we divide all the cars which are moving towards the right in as one set and all the cars which are moving towards the left as another set, so if we put all cars moving right in set 1 and all cars moving left in set 2, then any two cars which have a relationship should be of the form that one of them should be from set 1 and the other should be from set 2. Then if two cars have a relationship, then one of them should be in set 1 and other in set 2. That's it, right? So this is a very obvious thing, and somebody who has a very basic knowledge about graphs will very quickly relate it to a very basic property of graphs, that is graphs being bipartite. So if we make a graph of every two cars being in a relationship, that is if any two cars are in a relationship, then we add an edge between them, and if we do that, it will result in a graph. Then that graph should be bipartite. Why? Because in any edge of the graph, one of the nodes should be from the first set and the other node should be from the second set, and this is nothing but the property of a graph being bipartite. So we have just proved that if we add an edge between any two cars which have a relationship, then the resulting graph should be bipartite. And that's it, right? So this is a necessary condition for the answer to exist, but this is not a sufficient condition, it turns out. So yeah, first condition is that the graph should obviously be bipartite. So we will just make a graph. We will just ignore whether the relationship is of type 1 or type 2 for now, and we will make a graph and we will check whether this graph is bipartite or not. We will add undirected edges and we'll just check whether the graph is bipartite or not. So if the graph is not bipartite, we can simply output -1. So if not bipartite, so answer simply becomes no. So now I will consider the case when the graph is bipartite. I know for sure that the graph is bipartite. So any edge that I have in the graph will be from an R to L or from an L to R, right? So let's say we have an edge between U and V. Okay, so we have U and then we have an edge from U to V. Okay, so this edge will either be of LR or RL, right? So this edge will either be of type LR or it will be of type RL. So what I'll do is that if edge is, so like let's assume that without loss of generality, let's take U to be L. So like we have right now assigned the color to all the nodes. We know that the graph is bipartite, right? So what we'll do is that we will color all the nodes in either L or R. So all the nodes which are in set 1 will be colored L and which are in set 2 will be colored R. So we have right now assigned the direction to each and every node to each and every car, and so half of the problem is already solved now. So now we only need to assign their positions, right? Remember that we also have to output the positions. So now the half of the job which is left for us is to assign positions to the car. So now we have the graph, and we know that every edge is between one car in the left set and one car in the right set. That is, one car going to the left and one car is going to the right. Okay. Okay. So let's take U to be L and V to be R. So U is going to the left and V is going to the right. And now we have two types of possibilities. Either the relationship is of type 1 or the relationship is of type 2. Okay. So case 1, if relationship is of type 1. So you can notice that type 1 relationship means that they both are irrelevant. And if U is going to the left, then obviously V has to be to the right of U. We can see from here that U is going to the left, and so V has to be to the right of U. So this means that V has to be to the right of U, or U should be to the left of V. And case 2 is when relationship is of type 2. So in type 2 relationship, we can see that U is going to the left, so this right arrow is U, and so obviously V has to be to the left of U, right? That is the only case which is possible. So V should be to the left of U. Okay. So this is the only significance of the type of relationship that we have here. And now notice that what we are getting from here. So this graph is nothing but a list of relationships, and the relationships are of type this, that U is to the left of V or V is to the left of U. So every edge portrays a relation that some vertex X should be to the left of some vertex Y, right? That is what an edge is representing. So we need to output an ordering of these vertices such that all of these relations are satisfied, right? And this is where this problem becomes interesting, because it can be correlated with a very conventional and classical problems of graphs. And anybody who has some basic knowledge about graphs and has learned about topological sorting will relate very quickly. So there is this classical problem of having some courses and some prerequisites to the courses, and you need to output an ordering in which you can do the courses, such that if you are doing the ith course, you have already done all the prerequisites of the ith course. And that the answer to that problem and the answer to this problem is exactly the same, because this problem again is just the problem of assigning an ordering to every car such that one of the car appears before the other car. And in that problem, we have to output an ordering of the course such that you do one course before the other. And in that problem, what you do is you do a topological sort, and that solves the problem. So similarly here, the thing which we need to do is we just need to do a topological sort. So do a topological sort. But on which graph? How do we form a graph in which we do a topological sort? Well, it's very simple. So here you notice that in case 1, U should be to the left of V. So you add an edge from U to V. You add a directed edge from U to V. Again here, V should be to the left of U. So you add a directed edge from V to U. Very similar to the course problem, where if you have a course U which is a prerequisite from a course V, then you add a directed edge from V to U. So that is what you are going to do here. You will add a directed edge from U to V in case 1, and you will add a directed edge from V to U in case 2, and then you will just do a topological ordering of that graph. Now obviously a topological ordering will only exist if the graph doesn't have any cycles, and so if the graph contains cycles, then you will output no. Otherwise you will output yes, and then output the topological ordering of the nodes. And if you position the cars in their topological ordering, then obviously every condition will be satisfied and you will be good. So you have already assigned L and R to every car, and you can assign distances in the topological ordering. And that's it. That solves the problem. So let's just have a look at the code for better clarity. So let's see what I'm doing here. So first of all, we make this undirected graph, and we ignore the relationships for now. Okay. Right. And then what we do is Then we iterate on every edge, and if it hasn't been visited yet, then we call a DFS from it. And in the DFS, what we do is we color every vertex either with 0 or a 1, where 0 is representing L and 1 is representing R. And here we can also check whether or not the graph is bipartite or not. So if the graph is not bipartite, this OK variable will be false. And so after coming out of the DFS, if it is not OK, then that means the graph is not bipartite. So here we can simply output no. Now what we do is we will make a new adjacency list, the one which I have described here, in which I'll be either adding a directed edge from U to V or from V to U. Okay. So now what I do is I will iterate on all the edges and I will look at the color of U. If color of U is 1, then I'm swapping U and V. So I'm making sure that color of U is 0, which is L. And now this is the first case. If the relationship is of type 2, then as you can see, I'm adding an edge from V to U. So I will add an edge from V to U and I will increase the in degree of U. Similarly, in the second case, I will add an edge from U to V and I will increase the in degree of V. And now I will do a very classical algorithm for topological sort. I will take a queue, and if the in degree of a vertex is 0, then I will push it into my queue. And then I will keep iterating until I have elements in the queue. I will push out the front element of the queue and look at all the outgoing edges and decrement the in degree of all the outgoing nodes. And if the in degree becomes 0, I will push it into my queue. This is a very standard algorithm to calculate the topological ordering of a directed acyclic graph. So if the size of the topological sort is not n, then that means the graph is cyclic and a valid topological ordering doesn't exist. So I will output no. Otherwise, I will output yes, and I will just output all the nodes in the order in which they appear in the topological sort. So the node which appears first is assigned position 0. Similarly, the node which appears second is assigned the position 1, so on and so forth. So in this way, finally, I will just output my answers. So yeah, this completes the solution to problem E, which is all I had in mind today. So thank you so much for watching, and I will see you in the next video.